Okay, everyone. Welcome back to the third stream in this series about learning Rust and basically covering my learning curve and the problems that I encounter along the way in this relatively hard to learn new language. Been around for a while, but it's quite famous, I guess, for its learning curve, and I think so far, I have to say, the learning curve is not so much the language itself, like the constructs that it provides, but the patterns that you need to be aware of, and how the thing that separates Rust from the other ones, from the other languages, is of course its memory management system and how you have to think about memory um, and how this sort of keeps you fast and safe, but it does add complexities to your code and many sort of patterns that you might have developed in other languages throughout the years. At least in my case, you have to be reconsidered. And suddenly, some things such as ordering of variables also matters. We'll have a look at that today, I think. So we ended the last stream. Okay, or the goal of these streams is to make a simple epidemiological model. It's just the simplest possible one. We will simulate a bunch of people, and those people will seed some people there in that population that are infected, and then we will let them infect other people over time and then gain immunity. So this is an extremely simple epidemiological model. It has no clustering, no weights, no sort of sense of distance and so on. So we are, or from other people, and so the things are very simple. But what I do hope eventually to do is, I hope to have the ability to at least add some interventions so that we can, at certain points, we can like reduce the infection rate and see how that happens. We can adjust the R0, the reproduction number. But one of the more important things also in terms of learning Rust, which is the goal here, is to make it multi-threaded so that eventually we'll be able to make the simulation run faster, I hope. One thing I also do want to do is I want to create the same simulation in Python, and then I want to see how what kind of speed we get in comparison to Rust, if it does more or less exactly the same thing. Okay, so we will start this stream by adding. So I just have to keep an eye on some other things happening here in the background. Moving an apartment, and that means certain things have to be taken care of. Worst case, I will need to take a short break, but I hope we will manage to avoid that. Okay, so let's start by copying the model as it was in the last stream and continue from there. So the last stream, copy, yep, of course, okay, model stream 3. I will add these to GitHub, I think, once these various streams are complete, so that people can, or those that are interested, could have a look at these models that we have created, or these projects that we have created. There are more projects that I want to do. I want to do a graph processing system is one thing that I'm really curious about, and maybe do some of these like more not complex, but some of these design patterns that you know from other languages, like event-driven programming and channels, and well, some of these elements, it will be cool to try to make on these streams. So I hope I'll make a series here, both to aid my learning curve and hopefully to get other people either inspired, interested, and so on. Of course, I forgot to update the title of the stream. This is, of course, part 3. So I will update that right now. And here we are, and welcome to our first viewer. If you have any questions or comments, feel free to say anything you want in the chat. I always appreciate a bit of interaction in these things. Okay, so we're gonna move on to our let's see. So we're gonna open our model as it was, and then we'll continue our work on this model and see where we left off and what the problems were the last time. Okay, so we now have it here. So the epidemiological model works like this. There we go. It's over there. Streaming window. Okay, so the model works in the following way. Just a quick recap. we create a simulation and we say how many people are in the simulation. In this case, it's 10,000, although we do want to get up into the millions. Not that it probably matters beyond a certain number of people. You probably get the same results. So we will, but for now we'll leave this at 10,000 people, which is a small amount of people. Then we will. Then what we do is we 10 times pick a random person from the simulation and infect them, which means that we're now seeding infected people in our population. This is to get the simulation going. If no one was sick, nothing happens. Then eventually what we do is we loop for a number of days. In this case, it's 50 days. We loop the simulation to the next day. And the simulation doesn't have to know what day it is. But what it does is that it progresses the simulation, infects people or infected people, infect others, and so on, and so it goes on. So the most interesting part here is probably the way this works. And the way it works is that we have our population, okay, so a simulation, actually we're not really using this R0 right now, but we have hard-coded it to be 3, which basically means that every infected person infects 3 more people. So we can actually remove this. We should probably do that as well. We'll see if that gives us some compiler error. Some new takes. I'm just gonna correct that so we get the R0 away from here. Like I said, we're not really using that number anywhere, so we can remove it for now, since we've hard-coded it. But this would, of course, be a very important parameter if you want to do interventions and if you want to have, like if you want to study different scenarios with a model like this. I should probably add a disclaimer that I'm not an epidemiologist, but I am a scientist. I work in other things. Okay, so let's have a look again. Simulation is basically a collection of people. And we also added this sim info object. We'll see today if we can get rid of this, because I've learned some things that I think mean that we don't need this object anymore. In fact, we'll see in a moment why we created this and why there's also a person vector in sim info. But we'll see that in a moment, I think, that we will not have to use this after all. Okay, so the simulation is essentially a vector containing these 10,000 people. So what is a person? A person just has an ID. In fact, this is not strictly necessary. ID is also just use size, which is an unsigned integer of a certain size that is the maximum capacity of a vector in Rust. So use size is the basic type that's used for all vector sizes, as far as I understand. Each individual person has a status. The status is that person's state at that point. This is a basic principle that in these simulations is the person is either susceptible to infection, the person is currently infected, the person is recovered from infection, or the person is dead. We're not actually gonna, we could use this, but for simplicity, we're gonna say that everyone recovers. That is also a sort of a hopeful outlook on things. And I don't think the fact that some people die is so important for us, but we'll see. Oh, who knows? Maybe we'll add that. But then there will be a certain risk for every individual, whether they will pass away or recover from the infection at the end. Okay, so a person has that status. And what happens when the person gets infected is that the person has a clinical course. And a clinical course means that that's how the disease progresses in that individual. So we've also hard-coded this clinical course to be the same for every person. But effectively what it is a vector of sick days. So what is a sick day? So a sick day, the thing we're interested in knowing in this simulation is we're interested in knowing whether the person infects someone else on that day and how the last day concludes. So basically what each of these sick days can either be none, which means that that person infects nobody. It can mean that the person infects another person, and finally the last element is the conclusion of the clinical course of the condition. So as you can see here, you see these beautiful nested data inside Rust enums, which I love these. You can put variables on some of the enum declarations. It's cool. It's really neat. This is one of the favorite things about language that I've discovered so far. I don't think I've seen this anywhere else. Okay, so basically that's what it does. We have a new function that creates a simulation. We have a function here that picks a random individual, or picks the index of a random individual in the simulation. And then we have the next day function. We have a function in simulation to infect other people, and that's so far all we need. The problem is when we build this, we're gonna have it's gonna stop for us. And the error message that we get that stopped us the last time is you cannot borrow self as mutable more than once. Actually, we had a similar error message, the 506 was it? And at the end of the last stream, this made me think that so Rust's memory system says, you cannot borrow something as mutable more than once. So because you can either borrow, so if you have a variable x, and then you want to give that to another function, you can either move it into that function, meaning you have no longer access to it, or you can borrow it to that function, but in read mode only, which is just called borrowing. And you can borrow that variable to as many functions as you want. There's no problem as long as they are only read. And if you want to borrow it, borrow the individual variable as to be able to edit that variable. So let's say that you have a method that changes that variable, then you will borrow it mutably. And these are two different ways. I perceive this to be basically about read or read-write. And when you borrow something mutably, there's a limitation that says you can only have one mutable reference to a variable at any given time, but you can have as many unmutable references as you want, but you cannot have mutable and immutable references at the same time. And this is the sort of the core of Rust, is to avoid these problems where you don't know what happens to a variable before you read it again. So if you have a variable that might be deleted as a side effect of another function that worked on that variable, then you will have a 0 point, or you have a pointer to memory that is used for something else. And this is of course, the Rust core idea is to get rid of these problems. So these limitations of borrows are there for our protection. But of course, this made me think in the last stream that does this mean that when you have a method like infect on the simulation, you can then of course this method gets a mutable version of self, so it gets the simulation in here. But what I thought was that meant that, okay, but then you cannot call another method on simulation from in here. So if I call, so let's say that I take self and then I could, which is the simulation, and I wanted to infect another one, then I have to pass self into the infect function again, because this would be a cyclic thing, right? So maybe you cannot take mutable self and pass into other methods on that object or on that or other methods on that struct. But this is not actually the case. You can do that. So there are other reasons why our code fails. Okay, so let us move on. And today we're going to try to fix this problem. Our biggest problem, and learning how to do this now, it also sort of made it easier for me to understand that, yes, we don't actually need to think very differently about our data in this particular simulation than we would do in other languages. And hopefully by the end of the stream, I will have managed to make this simulation run, and we'll output some graphs to have a look and see what the simulation, how many people are infected at any given time, and so on. Okay, comment from Rainmaker in the chat, infamous coder man. Yeah. Well, I do like programming, and this is of course relevant for some projects I'm doing right now. How are you, Rainy? I think some people got confused and thought I was playing the video game Rust when I was doing these streams. At least someone jumped in on the first day and thought that was what happened. Okay, so the first thing we're going to do is we're going to fix this next day thing, and I'm basically just going to start over on this method and see if we can make it run. So the first thing that the first mistake that I made on the other time was basically, if I wanted to have one of the things that we need access to the people array here. So okay, so what we're going to do now is we're going to do the following. What do we do next day? Well, first of all we have to find all the infected people, because first of all we don't want to bother with the people that are not infected, because we don't need to look through them. So our first challenge is to take the people array, loop through that, but do it in a way that means that we will find and filter out the ones that we're interested in, and then we will deal with those individuals as we find them. and update their status. So we're going to try this now. So the first thing we're going to do is we're going to try to loop through the people array. So we're going to say self.people. So let's just try this first. So we're going to say for person in self.people. The first question is, can we do this? Nope, we cannot. Okay. First of all, we're just going to check that actually this compiles. So if we don't do anything on next day, does the system compile? Yeah, it does. It has lots of error messages here. These are just warnings, so they don't really do us any harm right now. So Rainmaker in the chat says that he is super addicted to WoW and busy with a job. And well, I hope you get a good job then. So I'm just curious, WoW, isn't that like very 2005? I remember that game coming out. I played it extensively for 2 weeks, like in 2005 or 2006. But it seems so different now. It seems like it's more filthy casuals. Is that what you are? Is that what you are, Rainmaker? Okay, let's continue. So one of our problems here is that, of course, we don't want to move people out of the array. So I think what we can do is we can just give a borrow of self people. Let's try that. It did, so we can run it now. So we can, now what we do is we get a version of person here, like this. And so next thing we, of course, we want to change these people. So we have to make them mutable. So can we do this? Yes, we can. So now we are allowed to do this. We're allowed to take mutable versions of person out. And now we're just going to check that we can actually do, can we set the status of these people? So let's say that we set their state to, let's say that we induce a miracle. So now we're going to make all of them healthy. And we can do that. So that actually works. This is sort of, this is really what we wanted to do. So I think in the last stream, I messed this up by adding too many different sort of varieties or sort of variables, and I got confused in the sequence of these variables, and that's why we got our error messages. And this is some of the same problems that we had down here in Infect. So we're going to simplify this function, and we're also going to look at why, because we had some trouble. We had to move the picking a random individual out of the simulation and into like this function in the simulation namespace. But I will try to fix this so that this pick random person is also just a method on the simulation. So we'll fix that in a moment. Okay, so let's continue. So here's the next interesting part. Now we want to make sure that these people are only the infected ones. So Rust has this beautiful thing where you can actually take this. You can take the iterator. Let's see if we can manage, or let's actually see if we can, I hope we can manage to do this. So what I want to do is I want to take the iterator and I want to filter it. What we're saying now is that we're taking all the people, but we are adding a method in an enclosure, an anonymous method that will give a true or false for whether this individual is part of the collection. So we'll take the person, and then we'll say we'll simply say is the person's status infected. Actually, it's state infected. So what this should do is that it should return another iterator. This is a very functional way of thinking about it. Let's try this. Okay, so failed to do. Okay, so that was actually an import that Sea Lion created there because I misspelled something. Okay, look at that. So we got scrolled away from our point here. So let's make this a little bit clearer by moving it over here. What we're doing here, this line here says that, okay, so we take the mutable version of the self people array, and then we ask for the iterator, and then we filter it using these criteria. And the criteria takes this anonymous function with a p, and the p is the element from that anonymous function, and then we say the status equals infected, and then what we should return with here now is only the infected people. So it does similar things. Like we could take this iterator and we could then say count, and we'll get a count of how many people are there, or we'll map and then we'll apply a function to several of them, and we can say any to get a true or false if any of those objects satisfy certain other criteria. So it seems like you can chain iterators. You can do really, really cool things, because the modifications like filter here adds another iterator from our iterator. So it's neat. I like this, and it makes me feel more like the kind of things that I do in TypeScript and JavaScript, where you sort of chain these things together. It also has a fold function if you want to sum up things. Maybe we'll get used for that later. So we'll say what we do now is get all looped. What we do is we loop through infected people. Let's see if we can get this to run. Can we now say that we will? I guess now we're going to magically cure all these people. Can we change them? Has anything changed, like in the code here? I don't think so. Let's try that. State. So we have, now going to just fix all the infected people. This beautiful medicine. Okay, so we get an error message. Cannot sign field of immutable binding. Well, so the iterator, I think, has to be mutable. Let's try it now. And it compiles and it runs. Okay, so we can ask for an iterator that takes immutable objects, or we can ask for an iterator that takes mutable objects. Okay. Here we are. We're getting closer to what we want to do. But we don't want to cure everyone, right? In fact, we want to make people sick. So we're going to continue on this. So the first thing we want to do is, okay, so for every time we do next day, we want to take the first. So remember that people have a vector of sick days that describes their clinical course. So we generate that when we infect people. So it means that, and because we simplified it, it means that we did a very simple version of it where every third day they infect someone. And we're also going to add on the final day, actually, of the course, we're going to add that the individual. We're going to add that the person is we're going to add the conclusion to the sort of disease progression, and that conclusion is going to be a state of recovered. The reason I'm doing it like this is because it could be in the future that we want to add that the person dies on the final day, or get the sequela, like it has some kind of fallout from this condition. So we'll continue this way now. Putting it like this adds a little bit of flexibility for us. So we'll do it like this. Okay, so the person that we now have picked out of our iterator has a clinical course. And what we want to do is we want to remove the first item. And we want to keep that item. So this is the current day equals like this. So now, of course, we could be in a situation where a person has no more elements in their sick day, or in their, okay, so that actually, yeah. Again, what happens here is that sometimes I misspell something, and then CLion imports something that makes the build fail, like it did there. So that's why we got an error message there. CLion, by the way, is beautiful for the debugging, at least. I've used Visual Code a little bit, but Visual Studio Code a little bit, but I think CLion it's super professional. It has amazing shortcuts. Okay, so now we know the status of the current day, and then we will now match the current day, and we'll use a little CLion trick again. We'll fill the match arms. So these are the things that can happen. So either nothing happens that day, the person doesn't infect anyone, or the person infects someone and their ID is here. We generate that in the infect function. That's predetermined. Then the other potential conclusion is that the person has a status change, means that either they get recovered or they die. Right now their status is that they are infected. In the beginning, like I said, everyone is susceptible. Then we infect 10 people, their state is changed to infected. They end up in this loop that we have right here because of this filtering function. And then they remain infected until we do something about that. So the conclusion is the final state. So that is the last state. Okay, so if we reach the conclusion that's the final day of the course of the disease, then we will update the person's status to the last state. So if the person recovered, then the person is now recovered, and if we do add mortality in the future, then people will pass away. Mortality is complicated because it is age dependent, right? So if you want to add mortality, adding just the risk is maybe not so interesting. If you want to actually get some interesting data out of our model, you would have to add like a distribution of people by a certain age and so on. This gets a bit complicated, and I'm not sure it aids us in learning Rust. And that's why I will not include that in this model. However, the alternative here is that the person infects someone. Right now, let's just see that this runs. We know that this runs now. So if a person infects another person, we should now be able to do self. Self here is the simulation. We're calling this on the simulation object. And then we should be able to do infect. And we will take the ID of that person that we want to infect. So let me just try and think if we can do this. What I'm concerned about here is that we are inside this loop. We are using an iterator based on self. And I think that this means that we will now borrow the simulation one more time, and that will not compile. Here we go. Cannot borrow self as mutable more than once. Let's have a look at what the error messages in Rust are really descriptive. I think they spend some time on this to clean these things up. So let's see what happens here. So yeah, so here is our iterator constructor, and it says first mutable borrow occurs here, first borrow later used here, and then second mutable borrow occurs here. So I think we might need to do something about that. It has a very simple solution, but I'm also going to just try. I'm just going to try these things because sometimes it surprises me if we do this, that it sometimes compiles, but it doesn't. Yeah, so we are not allowed to borrow ourselves to another function inside this function because we are already mutable, and we can only have one mutable reference to self. That means that we cannot actually call this function until this iterator goes out of scope. And that happens after the for loop. So it means that as long as we don't reference person further down here, we should be able to call infect on self after this loop is completed. That means that we'll collect these values and try to run it again. So we will create ourselves a mutable vector. We're going to call it new infections, and that will be a vector of actually it's IDs, and then we will just create that vector like this. Okay, so now instead of calling directly now, instead of calling so we need to free this we need to free this mutable borrow before we can use it again. So we will simply collect these. So we'll say new infections, push, and we'll push into that area, we'll push the ID, right? Okay, so ID here is a copy type, so we are free to do more or less whatever we want with it. But we're creating a copy every time we do that. So let's see if this runs. Okay, it runs. So now the next thing we're going to do is then. Okay, so now after we're done with this iterator, this person and this iterator should now be out of scope. This is how Rust memory management works, right? When something isn't used anymore, it's dropped. Sorry, just gotta check my messages. Yep. Okay. So now we will loop through the new infections that we had for ID in new infections. And in principle, I hope we should now be able to do sim infect. No, it's actually self infect and then that ID. Who do we pray to make this work? Do we pray to the logo of Rust or the makers of Rust? And our prayers are answered. It did indeed compile. So this, I think this shows the Rust memory management a little bit. So this is what I mean by those new patterns and new ways of thinking. Okay, so how does this work? I think, and why did it? So I understand why this works. We're passing ourself as mutable. We're passing this mutable self into this function here. So it means that while this is active, we cannot do that again. And again, it means that the reason is that if we okay, so what is the reason here? So the reason normally would be that we don't want to have any references to self. We don't want to have more than one mutable reference to self at any given time, so that two processes or two methods could edit that variable without or at the same time, and that therefore causing it to deallocate or change in a way that would cause a race. So would it be so bad here to do it inside? I guess it could be that this iterator could deallocate self. In principle, it could clear that memory. And then when we called, infect on that, we would be passing a pointer to where that simulation used to be in memory, and then we would have the problem that we don't know what this iterator does to that. We don't know what the iterator here that we created here does to self. I guess in principle you can clear self if you want to, but I think Rust has some protections against that as well. But once we are done with this, then we don't have a problem, because now we can use self as much as we want here. And because this happens in every iteration of this loop, it's always only one time that we are using self. So you will never have a conflict between methods that can edit this thing. I think this is how I understand how this memory management works. And I guess it's probably valuable. Like I'm not really a systems programmer, so for me, some of these complexities are complexities that seem, there are problems that I haven't had because I haven't been dealing with manually managed memory for many years. But now we have actually done what we tried to do. We are infecting individuals. So in principle, we are also saying that we are curing the people at the end. They are the last status update should be, as we say here, the last status update for every single one of them is that they are recovered. So now if you run the simulation, well, we're not outputting anything. We don't know anything about the numbers that are happening in here, right? So it would be interesting now. We're gonna, at the end here, when we have infected all these people, we will, for each single day, we'll count up how many people got infected. We'll log this data and we'll make a table out of it, a CSV table, so we can make some plots. But for now, let's just dump the numbers and have a look. Okay, so what we want to do is we want to count the number of susceptible people. So we call those sus. So we're going to do, and again, these people are in the people area, right? So we will do self.people. And now we'll do the iterator. Oops. We'll get the iterator, and then we'll filter so that we have the people that are susceptible. So we'll do the same thing as we had up here. We'll take the P, and then we'll, okay, this gets quite long actually. So I'm going to run off the edge here. We're going to say, so we will keep the ones where P equals status, or no, state susceptible. And then finally we'll count how many that is. Okay, so that should work. This was a bit messy. You could probably simplify this by, you could write a function to count. This is like a long, nasty thing, right? So we should count the number of people in our, we can actually do that. We can do a public function count state, and then we'll pass into it. And actually we can just pass self. The question is if we can call this from the next day function. That'll be interesting to see, or if this has to be mutable for us to be able to do that. Okay, it's not public Facebook, it's public function. So we'll pass just self, and we'll pass the state we're looking for. So we'll do state, and that is our status. This is a little bit messy, this terminology, but I hope it's right. Okay, so, and we will have this return, and it will never actually be a negative number, so we will return an unsigned. And then instead of allocating this like this, we'll do that, and it's neat in on the use size. Okay, so so we'll simply cast that. I think we can just do like that. So you don't need to put a return statement, which is cool. The last expression is the return value unless you put a semicolon at the end. It's a funky rule for us that are used to either or semicolon terminated languages. Recently doing some Kotlin, I was spoiled by the idea of not having to terminate sentences with a semicolon or statements with a semicolon. Okay, so this counts susceptible. Does it compile? No. Binary operation cannot be applied to. Yeah, of course. We are just comparing person, but we want the we want the person dot state status. Yeah, that makes sense. Compiles. So we are allowed to. So in this sense, self is not mutable. So okay, self is not mutable. So somehow we are allowed to pass, even though we are sitting in this method on a mutable self, we are allowed to pass an unmutable self into this one. That is interesting as well. That's an interesting observation, because I was sort of thinking in my head, very simplified, that when we are having self as a mutable variable, we would not be allowed to pass that into it. But apparently we are. Just for now, we are going to, we're just going to print out these values. So we're going to, we're going to keep it very simple now, but we want to have this end up in a table. Because if we run the simulation now, we'll get the number. Oh, look at that. We will get the number of susceptible people. And you see that is dropping dramatically towards day 50. That is actually really cool. Okay, so let's, on the next day, I now also want to pass in what day it is. So the day will be also a U32. We can never have negative days in this experiment. And then we will take the, when we are looping through here, we'll take day and we'll pass it in. So in main, again, we are looping through 50 days. So we'll pass the current day into the simulation. It seems here like there's still dynamics in these numbers. So I think we have to go for 100 days to get sort of some level of stability towards the end. So we'll loop for 100 days from now on. And then we will actually, we'll also print the number of the day like this. Here we go. So, okay, so what we see is that in the beginning, we have our 10,000 people minus 10, which are the 10 that we seeded in the infection. And as we are going down, we see they slowly change here, and then we're talking 1,000 a day that become become infected effectively. They're dropping out of the susceptible pool, and eventually it reaches a level of stability, which is sort of a steady state here. Not a steady state. It means that there is not enough people in the simulation to infect that we get infections, that we get any changes in the susceptible individuals. Okay, so we're also going to count the number of active infections. So we're going to call that inf, not for infinity. So we're going to count the number that are infected, and then we're also going to count the number that are recovered. We're going to call it rec. So we're going to print the susceptible, the infected, and the recovered. Okay. Go. So at the end here on day 99, nothing happens, right? But up here, you should now see that initially, okay, so itar is the same numbers 3 times, so I'm doing something wrong. Yeah, of course, here I'm not actually using the status. That was stupid. Rust does not protect you from stupid mistakes, but it may protect you from complex mistakes. Okay, so actually we now have our simulation running, which is neat. We can see, just looking at these numbers, we can see exactly what happens. In the beginning, we have 10 infected. and then they dramatically increase towards the middle, and in the end almost everyone is recovered. But you can see that a lucky few, there's not 10,000 people in this group, 583 people dodged the infection here. So it means that there is a small percentage of people that were lucky. They were lucky enough that they were not randomly infected in this simulation, and at some point in the infection, so many people were immune that it was impossible for the infection to reach these people that were left. So that is an interesting sort of observation of this. We can just in this very simple model, we can observe this event that some people just don't get it, not because they are immune, but because too many other people had it before them. Okay, so that was an interesting thing. Now we're getting this data out. We should probably, since we're getting it running now, we should probably put this into a table and make it a nice little graph, right? So what I did was I found this library, this crate called Pretty Table, and I think we will import this one and use that to print. And the reason is that it has this sort of iterative syntax. You can create a new table and then you will add a row to that table. So that's basically what we're doing here with the commas, right? We're just dumping it here. We could just copy this text, but it is neat if we actually export to CSV. Then we also get to try how fast and efficient that is. Okay, so let's take the TOML file, the cargo file, which includes the dependencies, and the cargo, the build system will automatically download the ones we do. So we'll try pretty table. Not reach crates.io. Okay, that's good. Let's go pretty table rs. There you go. This is the one we want. Okay, so we're going to import that. So we're going to use pretty table. Will it be like this? Can we actually do that? Let's build this and just see, because now does it include it? As now it should include the new crate that we have created, that we have chosen when we build. Yeah, there we go. And then we will use pretty table. Okay, this is pretty table, and we will use yeah, we will include, I think we will include table, I understood, and then there was a macro to create a table. Maybe we don't need that one. Let's just use table for now. Okay, so the next thing we want to do then is we want to create a table that we keep in our simulation during the days that are going. So can we have an empty table? I guess we can. We can just try to add that table. I think let's have a quick look at the documentation here. So we will just use table new. And then we add row, and then at the end we can either print it out or we can save it to a CSV, as it says down here. So let's just try that. What we'll do is we'll create in the simulation, we'll create an output. There'll be a table. Nice, output. And the simulation has a construction function or a factory function called new. So it means that when we create a simulation now, we have to create a new function. So we will add the missing field, which is output, and then we will take table new. And as far as I understood, we didn't actually need to specify columns or anything like that. Let's just see if our model runs. It runs just fine. So instead of doing this now, we will add these numbers. So we'll do self.table, no, output, so we call it. Row, and then we will, did we have, how was the syntax here? Yeah, so it is just, see. Yeah, so we actually create, okay, so we use a macro called row, and then we pass it the values that we want. So let's just do row. And then we give it day, sys, inf, and rec. And let's try that. Oops. Cannot find macro row. Okay, so we probably then have to import it here. Row, yeah. build now. No, sell. Can we just import everything? Am I being naughty now? That's really naughty. But I think the reason you don't want to do this in general is because you don't want there to be any misunderstandings about where things come from in your imports. But it floats our boat right here, so we will we'll just do it like that. Okay, so we also want to have a header, I believe, in this table. So we're also going to say that if it's the first day, we want to add a row that includes the titles that we have in here. So that will be day susceptible, infected, and recovered. Okay, let's try that. See that it runs. Yep, so now we didn't get that nasty output we had here. We can also remove this line where we say that we are infecting people because we're not so interested in that. And then here in main now, we're now gonna, once we're done with this, we will take sim, we'll take the output, and we can print it. Print standard, is that what we want? Then we'll get a table, I hope. And there you go. And now we do have a tabular format here. That crate worked just fine. Okay, that was a nice experience. We found a crate that we liked, which is basically a package, and we plugged it in and it just worked. That was actually very nice. Really unproblematic. And I hear really good things about Cargo, this build system for Rust. Yeah, that was nice. That was neat. We could probably prettify this so we specified what we were importing, but I don't think we're going to do that now. Okay, so let's save the output to a CSV file, and then we will have a look at what these graphs actually look like. So then we had to find a function for that. I think it was just let's see, CSV. Yeah. So we were looking for, yeah. So we can just specify a file, and then we. Oops! Someone's calling my door. I have to be back in one moment. All right, I'm back. Sorry for this rapid little departure there. We had one of the neighbors come down after an incident out on the terrace with some water running down from their apartment, but it has been resolved. Where were we? We were gonna we're gonna output this file, and then we were going to make ourselves a beautiful graph from the output of our simulation. Okay, so we need to import this file object, and we're gonna find a path to put this. So I think we're gonna do, is it home? I think I put it on Knut, and then we have desktop. There's nothing there right now, so I think we're just gonna take that. We're gonna take this and we're gonna put it like that. We're gonna do results.csv. Okay, that was it, right? So we can then do the sim.output.toCSV, and then we should be ready to go. Let's try this. Oh, where was why is it there? Where did that come from? Did I put it there? Oh, okay, here we go. So we have problems. Oh yeah, of course. We're not doing any error checking here. I'm gonna assume now that we can just skip the error checking. So I'm gonna do unwrap, and then we should be able to go. That was fast. Let's have a look and see at our desktop. And do we have a CSV file? Yeah, we do. Look at this. So now we can take this data and we can import it here. And we have our data in LibreOffice. This is the data we have already looked at. But of course, what we want to do is we want to take these data that we have here, and we want to make some graphs which are easier to understand. So let's take, we're going to plot day versus susceptible. And then we're going to take, afterwards, we're going to take day versus infected. So we can now make a chart. We're going to make ourselves a nice little plot here. And look at that. We are indeed getting these sort of sigmoid curves, or these nice looking curves, which show sort of the dynamics of the infection. Can I add a title to this graph easily? Doesn't really matter. Okay, so then we'll also have a look at this interesting thing, which is day versus infected. Not versus, but day on infected. We're going to chart that. And we're going to get like that, yeah. And now we can clearly see these patterns that we are used to. So if you did a cumulative, let's see if we can get we can actually just move this over here now. So this illustrates, of course, what happens if the infection just runs wild, right? If it is allowed to run its course. Here you see that the number that are susceptible goes down, and you get a chunk of people here that stay susceptible because they are healthy. And in fact, the people that are recovered are the people that have had the disease. So of course we can plot that too. So we're going to do a chart again for these guys. And this starts, of course, to look like the kind of plots that we are seeing in the real world now with the COVID-19. So actually this plot here with the susceptible is not really that interesting. But these two plots are probably. You can see this is effectively how many infected people you have every single day, and you can see that it does go up. And this is, of course, the number of cases that you have had. In our case, people don't die, right? People continue in this. People continue to live on in the simulation as recovered. We're not counting deaths, but in the real world, a certain percentage of these people would be people that died. If the infection had a fatal outcome, at least, or had some chance of a fatal outcome. So here we are. We have successfully created the simulation that we were trying to make in Rust, and it does output for us sort of what we expected. So I think this was an interesting. It's been an interesting ride to see this. So the final thing that I want to do now that we know that the model works is that I do want to clean this up a little bit. I think the next interesting thing to do now is look at what happens if we increase the population count to a very, very high number, and then it will be super interesting to compare this to the same simulation but written in Python. So these are some of the things that I'm really, really curious about. One of the benefits of Rust is, of course, this enormous speed increase that you could potentially get. So it would be cool to do that, and also to look into how we could multi-thread this. So let's see at our plan here. Yeah, so we have, yeah, that was actually one thing that I wanted to do. We have plotted the epidemic development. So we can take that out of our list. Yeah, I think I close the panel here. That we have done. We have exported the data to CSV. And the other thing that we messed up our code a little bit the other time, because there was this, I had this idea that it would be very, very hard to use this mutable self, or we had trouble using self, because we would then to infect people and to pick a random person, because then we would have to pass the self variable as mutated again, and so on. This gave us trouble with the borrow checker. But one more thing we will do is we can clean up this simulation a little bit and remove those sort of artifacts of the way I was thinking back then. And then we will also have a look at one more interesting thing with how the sequence of how you do things matters in Rust. It would also be good to modularize this, but we'll see if we'll do that as the very, very last thing. Okay, so the next thing we wanted to do is again to tidy up things a little bit. So right now we have this function called pick random index, which takes a simulation info. And one of the questions that I have here is, can you get rid of the simulation info in the situation that we are now? Because that would clean up our thing a little bit if this was just a self. This was a method on self. The other thing is this infect function here. This one relies, as far as I remember, on the info, doesn't it? Yeah. So it relies on the info, on the simulation info here, to pick this random person. So I want to try to get rid of that problem. I want to try to get rid of this of this construct here. Although there's probably nothing wrong with it. As far as I understood, we can revert this to use self. So the first thing we're going to do now, so now everything compiles. We know that the export works. Can I re-export that file? Yeah, that works. It probably just overwrites the file that I made. So let's get rid of this sim info thing and just do and self. Because what we actually do in this pick random individual is that we don't want to push anyone out of there, because we don't want to borrow something from this function. We want to just give it the index so that it can be recovered by later functions. And the index is a copy type, so we don't get into the problem that we have borrows going on of people inside the simulation. So we will pick a random index by getting just using random, which of course gives us something between 0 and 1, and we'll multiply it by the people in the simulation -1, and we round that and export that as a usize, because that's the index, the type of index that we have. We can actually export this as an ID. They're the same. These are just aliases that I've given, because we don't necessarily talk about usizes. We talk about individual IDs in this simulation. Okay, so we're going to take, instead of using info and n people here, we're actually going to look up how many people we have. So we are going to take self.people, and we're going to look at the length of that area. Okay, so this should work, right? So of course, then we have to modify the places where that is done. So we're going to take here, let's say in the beginning here, where we pick 10 random people, this function no longer works, so we have to modify it. In fact, we will now use sim.pickRandom index, and this doesn't take a parameter anymore, so I think this is much cleaner. There's probably situations where you would want to do it the other way, but right now we can just do this in this fashion. Okay, so the next thing we want to do, I'm just going to check my messages here because we are waiting for a delivery. Yep, it's fine. So this part here should now work, but the last time we did this, we had some trouble with it. It's not gonna, so what we will do now is we will try down here to do the same thing. sim.pickRandomIndex. No, actually it's not sim itself. There's no sim here. And now we're gonna have the same problem as we had. Okay, cannot borrow self as immutable because it's already borrowed as mutable. This is our this is one of those typical Rust errors, right? So let's have a look at what happens. And this is a little bit interesting. Let's first see what the infect function does. The first thing we need to know is we need to know if the person that we are trying to infect is susceptible. We need to know that, and because we are given an ID, we need to get the state of the person. We need to get the person based on the ID, and then we need to check if the person is susceptible. If the person is not susceptible, that is, the person is recovered, dead, or having the infection at the moment, we don't do anything. This is, of course, exactly the reason why you see this development in the epidemiology model. More and more people are not susceptible to the infection, and then it starts to drop. This is the herd immunity principle, right? Of course, if you let it play out like this, you will have a lot of dead people usually. In this case, it's benign, right? Everyone recovers. But in the real world, you probably don't want this completely rampant development. Okay, so the problem here is that because we need to get the person, we are now getting the person as mutable up in the beginning. We look for that. So we ask for a mutable borrow, and then later we ask for an immutable borrow because we are passing self into this function as we were doing up there. Okay, so let's have a look at what happens. So we have our pick random, and we are passing self into this function as the first parameter because we need to know the length of the people list in this function. Okay, so that's the problem. Is not that we are doing that. The problem is that we have this thing here. We have this mutable person reference that we used here, and that is still alive because we use it again down here. If this person is found to be susceptible, then we mutate the person down here after we have created in this function the clinical course. So we create those sick days in a vector. What is interesting here is the problem that we have is not that we are so one thing we could do to make this work is that we could simply, actually we're no longer using the sim info, so this line we can remove. Okay, so now let's just check this now. Now it doesn't compile, it doesn't run because of this reborrowing. But what happens if we create a course before we look up the person? Boom, it runs, right? Because here inside this iterator, we are picking random individuals to infect. So what happens is that when every third day, right, we infect a new person and we get to pick randomly who that will be. So we're passing self immutably into pick random index, and then we're getting the index back. And then once we've done this, we have removed that borrow. We no longer borrow pick random index is no longer borrowing it, so that borrow is cleared. We don't have that problem anymore. So once this is run, there's no more borrows of self. And because there's no more borrows of self, we can ask again here to borrow self mutably to get this mutable version of the individual, to look for susceptibility and set the course. But of course, so actually it runs now, right? This is fine. But the problem, and the reason this is not fine, is that every single time we infect someone, we're now performing this code to create the course of sick days, even though it might be down here that we'll just throw that away. So why are we doing that, right? It's because we have to borrow the person mutably here to be able to make these changes. And we cannot also borrow the person here while we are doing those things. So I think the answer here, and of course this is, it seems like overhead, but we want to check if person is susceptible first. So we will actually borrow we will first borrow the person as immutable because we don't need to. Okay, so now we have the person object, but because it's reassigned here, it gets dropped. So let's have a look. Actually, let's just check what happens now. Then we will take this, the check that we are doing, So what we're doing is we're saying we will first check the person, see if they are susceptible. So we will get the person and we'll just ask it as a mutable reference. And then we'll check if the person is susceptible, then we go on. If the person is not susceptible, then we return. We don't do anything more at this point. So only susceptible people will go on. Every other status of the person that we acquired from the index will just return. So nothing happens if they have been infected or are infected. At this point, this will no longer be used until we get here, so it drops off. Let's see if this compiles. This compiles. So we have now modified this. First of all, we got rid of the siminfo thing that we created in the previous stream. So let's just get rid of that. Siminfo. We don't need this construct anymore. Although there's certain, let's see if it builds. Maybe we're missing something. Siminfo not found. Where are we having it? Yeah, so the simulation siminfo, and then we will remove this because we don't no longer need to create that. And now it runs and compiles. Okay, so we have then taken out this particular problem. The siminfo is gone, so we have cleaned it up, and we have learned. This is really a lesson about Rust, isn't it? The way that you need to think about your variables in this way and these borrows is completely different from anything else that I've ever thought about. So this is difficult, but once you do it, it makes sense. I understand that you can do it, and the idea here is, of course, that this kind of manipulation is a trade-off that you have to have this non-garbage collected, completely memory-safe system operating for you. Okay, nice. So we have done that, and then the last thing we want to do, yeah. So we have taken the pick random index and we have made that on self again, so we don't have that other syntax with the where we use simulation and then double colon. Last thing I think I want to do with this simulation today, let's just see if there's something I forgot on my list. Yeah, so we have reverted to unmutable self. Interventions, not sure I have the time to do that today, but the last thing I want to do is I want to modularize this code a little bit, because simulation runs and that works, but right now it would be nice to have at least the simulation as a separate module. I was thinking earlier that person would also go in a different module, but maybe that is not so nice. But it feels sort of dirty to have main and the simulation in the same file. So I think we're going to create ourselves a new Rust file, and then we're going to put the simulation in there, and then we'll call that as a module. And in that sentence, I will also mention one thing that surprised me negatively when I was, it doesn't anymore, but it was something that I fiddled a bit with to understand about modules in Rust. So we're simply going to create a Rust file called simulation, and it's rs. Yeah, so notice this is a nice C-line thing. File is not included in module analysis tree. Analysis is not available. So it means that this file is not part of the current project because the entry point here, main, doesn't import it. So we will import our module. We will use simulation. And if I remember correctly, then this should now work. Does it? Basically, modules are just named like this, but actually we can try to add, just check that it works before we move anything more. We're going to create a struct. It's going to be a public struct. I think that's how you have to do it when it's in the module. Public struct called test. A bit bigger. That's it. It doesn't contain anything. I think I can now use simulation test. Can I? No, I cannot. Okay, interesting. Let's try and create a test. So the first thing we do is let t equals test. Something tells me this is not working. Undersold imports. Do I have to use create? No, that didn't work. Ah, of course it's mod. Sorry, I was thinking the wrong thing. So we're not, yeah, of course. The reason it says here that it's not included is because we're not actually using the right thing. We want to use mod simulation. And now that goes away. Okay, so what happens is that when you write this, it goes and finds that file and includes it somehow. I'm not sure if it's the file or the elements that are in there. So what we've done now is from the starting point of main, we say reach out to find these modules, and we found simulation. Test is not imported, however. But I think if we did simulation like this, then it is imported, and now it runs. Yeah, so that works. Okay, so now we have our module. So of course, that's the difference between mod and use, right? Now we could use simulation test, and then we don't have to write this anymore because we are importing that object into our simulation. So this is what we this is into our main file. This is what we want to do. We want to for now we can just import everything because it will simplify this. Then we'll grab all this code that is particular to the simulation, and we'll put that in our simulation file. So now the thing is that these things are not public. We have someone in the chat that should be banned, I guess. Actually, there's quite a lot of these messages in the chat now. That is a bit annoying, but that's okay. Okay, so we have put this these things in that module, but the problem is that we have not told anyone what is public. Like for instance, here simulation is private. So we can just ask CLion to do this for us, but for the sake of this, because we're looking at it, I think we'll just make simulation public. What else do we have to make public? We have to make, I think we have to make these fields public. So we have to say that these fields are public, like this table. Okay, so of course, because we are now we're not using pretty table here anymore, so we will have to import it here. Use pretty table. Okay, does it compile now? And a file function random in this scope. Yep. So we also have to move in some of these imports that we've been using. I haven't mentioned random so much. I think in the first stream we took that one in. So we're going to use random. Cannot find structurable test, of course, because I removed it. So we're not going to use that anymore. How is this going to be? Yeah. Okay. Closer. Private type in public interface. So that's simulation person. So yes, indeed, we have to go down and we have to make our person public. See, it compiles and it runs. So now we have our main file. Let's zoom out a little bit here. And we also have this simulation file, which includes then, let's see if we can we split this view so we can see that in a separate vertical window? Yeah, we can. Okay, so we have these two files that are now like this, that are now the modules in our simulation. So I think for now, this is actually pretty good. We have achieved what we wanted with the exception of the multi-threading, and we also want to potentially move on to we also potentially want to move on to adding interventions to the model. But again, that's an interesting exercise to do for the sake of the modeling itself. But considering what we are trying to do here, which is to learn Rust, I think it's much more interesting if we are adding the multi-threading to see if we can speed up this simulation. I don't have time to do that today, though. I think I'm gonna call it for this stream. We have arrived at the first goal. Next goal again, splitting this the next day function into threads so that one will process and infect multiple people. But there's a bit of a challenge there, right? Because you cannot, because every infected person needs to be able to pick from the rest of the population that we have in our simulation. So you cannot just take the people array and split that into multiple different arrays. So you have to have some kind of synchronization of access to that. And that is what I actually started with on the first stream. So in the next stream, we'll try to make a shared reference to the people array that the multiple threads can access and read and write from at the same time in such a manner that it is synchronized and safe, and that it will update the simulation. And we will try to time that a little bit to see if we can get it to go faster than if it is single-threaded. Maybe we will actually learn that the overhead from that operation is heavier than what we gain from the simulation. Although I don't think so, because we will split out the work of infecting these people in multiple cores, and especially if we add a high number of people to the simulation, this will be interesting. Right now, only 10,000 people in the sim, so we are just at a very, very low number. I think we will at least get it up to the level of people that we have in Norway, which is roughly 5 million. And then we will see how it develops. Okay, but to anyone watching, thank you very, very much. I hope this was interesting. Whether you're watching it on YouTube or Twitch, if you have any comments on YouTube in the future, please do leave them below. And I think I will publish this this simulation, or the projects as they succeed. I will publish them on GitHub, and I'll put the address down below the videos. Okay, thank you for watching. That's it from me today, and have a good day.